In this next video, we'll demonstrate how to modify the base model to achieve maximum alignment with real-world heater conditions. But before we dive in, let me highlight a specific FHinfinity capability for vertical tubes. To do this, let's go back to the process fluid pressure profile curve. You might notice the pressure fluctuating up and down. This is because we've accounted for static pressure drop inside the tubes. For vertical tubes, FHinfinity allows you to define the flow direction in the first pass, either top-down or bottom-up. Let's reverse the flow direction and see how the results change. But first, I'll adjust the output chart settings to display only the pressure profile after the run, keeping the view clean. As you can see, the pressure profile has changed completely. Naturally, if we were to ignore static pressure drop, the pressure curve would be smooth, without these fluctuations. Next, let's add coke to the tubes and observe its impact. We do this via the coke and fouling page. In FHinfinity, you can assign specific fouling types to individual firebox tubes, both inside and outside, or apply uniform values across all tubes. For the convection section, you can define these parameters row by row. For this example, I'll assign petroleum coke to the inside of tube 6 in pass 2. Then, for tube 3 in pass 4, I'll add iron oxide with a thickness of 2 millimeters. As you can see, the pressure profile across the different passes has changed significantly due to the reduced flow area. Other parameters have shifted as well. Let's take a look at the vapor fraction profile, for example. We can also compare the new tube metal temperatures against our previous results to see exactly how fouling impacts thermal performance. It's important to note that, unlike other simulation tools, FHinfinity provides both tube metal temperature, TMT, and skin temperature as distinct output parameters. When no outside fouling is present, these two values are identical. However, when external fouling exists, skin temperature represents the temperature at the outer surface of the fouling layer, the value you would actually read with a pyrometer during field inspection. Meanwhile, TMT indicates the temperature of the underlying metal tube wall, beneath the fouling thickness. Now, let me highlight another key advantage of FHinfinity, the path imbalance feature. To keep things clear, I'll first restore the model to the previous snapshot, removing the coke and fouling settings so we're back to the clean base case. In real-world heaters, it's common for flow rates to vary across different tube passes. FHinfinity lets us replicate this exact condition. For this example, I'll distribute the total flow across the 4 passes using these ratios: 0.9, 1.0, 1.05, and 1.1. Let's run the model. As you can see in the pressure chart, the effect is immediately visible. The passes carrying higher flow exhibit a correspondingly higher pressure drop. Next, let's switch to the temperature and velocity profiles. But before we do, I'll take a quick snapshot of this imbalance case so we can easily compare it with our original uniform model later. In this graph, the red lines represent temperature, plotted against the left axis, while the blue lines show velocity, referenced to the right axis. You can clearly see that each pass now behaves differently. If we compare this to our initial balanced model, the difference is striking. Each pass responds uniquely to the flow distribution. This level of granular control makes FHinfinity uniquely suited for accurately simulating and troubleshooting real-world operating heaters. Before we continue, this is a good opportunity to explain how charting works in FHinfinity. To keep things clear and avoid clutter, let me draw a single parameter chart, for example, peak heat flux. The horizontal axis represents the process fluid path. It starts from the left side with the convection section tubes and continues through to the firebox tubes. Those breaks or gaps you see in the chart indicate transitions between different heater sections as the fluid moves through. In this case, we have two tube banks followed by one firebox section. Now, there's an interesting detail in this heat flux chart. Notice that rows 11 and 6 in the convection section are showing peaks. Why is that? Let's take a look at the tube's data page. As you can see, these two rows have a larger longitudinal pitch. Likely the designer increased the spacing here to accommodate an access door. We can verify this visually in the 3D model as well. Because the longitudinal pitch has changed in these rows, the gas side heat transfer coefficient, which FHinfinity calculates with full precision, doesn't follow the general trend here. This is exactly why we see those peaks in the chart. This level of detail demonstrates that FHinfinity captures real physical conditions with high accuracy. Now that we've discussed accuracy, let's take a closer look at the settings page, where you can customize calculation methods to align the model even more closely with real-world heater behavior. For calculating the process side heat transfer coefficient, HTC, FHinfinity offers two options: the API 560 recommended method or FHinfinity's proprietary package. The proprietary method calculates HTC by explicitly accounting for both the heat transfer region and the flow regime. A critical distinction. While this level of detail may not drastically change overall heater efficiency or outlet temperature, it has a direct and significant impact on tube wall temperature predictions. Let's verify this. The red curve here represents HTC, while the blue curve shows peak tube metal temperature. If we overlay the heat transfer region profile, we can see the flow evolution. Starting in a convective to liquid state at the inlet, transitioning to subcooled boiling in the lowest convection row, and then shifting to film boiling from tube 5 onward in the firebox. This transition drives the sharp rise in HTC and, correspondingly, the drop in peak TMT. Finally, in the second-to-last tube, the flow enters a two-phase forced convection region, which explains the secondary peaks in both curves. If we compare this result to our earlier model using the API 560 method, the difference is clear. The proprietary FHinfinity approach captures the nuanced physics of the process far more accurately, bringing the simulation much closer to actual field behavior. Another important setting available on the settings page is the control of imperfect stirring in the firebox. This can be adjusted using either the Hoddle bridge wall parameter or the temperature increment method. In our pre-filled model, the temperature increment was set to 67 degrees Celsius. Using the heat balance report, we can see how this value distributes efficiency between sections: 51.7% for the firebox and 21.4% for the convection section. If we want to view the firebox temperature and bridge wall temperature based on this heat distribution, the combustion report shows them as 931 degrees Celsius and 864 degrees Celsius, respectively. Now, let's consider a real-world scenario. Suppose the actual firebox exit temperature measured in the field is 895 degrees Celsius, while the overall heater outlet temperature remains unchanged. To match this condition, I'll adjust the temperature increment to 28 degrees Celsius. And I'll also enable the temperature controller on the heater outlet to maintain the target output. Then, let's rerun the model and see what changes. Alright, the results are in. The bridge wall temperature has increased from 864 degrees Celsius to 895 degrees Celsius, aligning with our field measurement. Checking the heat balance report again, we see the firebox efficiency has shifted from 51.7% to 49.8%, while convection efficiency has increased from 21.4% to 22.6%. In this example, we made the adjustment using the temperature increment parameter, but the same calibration could alternatively be achieved using the Hoddle bridge wall parameter. This flexibility lets you tune the model using whichever field data you have available. Now, let's explore the auxiliary equipment you can add to your heater model in FHinfinity. First up, the transfer line. In this example model, we've defined 6 sections for the transfer line, but keep in mind, Users can add various components from the library and assemble them to match the exact physical routing of their actual system. This flexibility ensures your model reflects the real-world layout. Let's run the model with this addition. I've also adjusted my preferences in my FHinfinity so that the velocity and temperature and pressure charts display automatically after the solution completes. As you can see, the charts now include an additional segment corresponding to the transfer line. Likewise, reports such as the process side hydraulic report have been updated to include detailed section-by-section data for these added components. This seamless integration of auxiliary equipment allows for end-to-end modeling of your entire thermal system, giving you a more complete and accurate picture of performance from furnace inlet to downstream equipment. To convert our model to a forced draft system, we simply change the burner type in the burner data section of the Firebox arrangement page to forced draft, which can be configured either with duct or without duct. For the forced draft zone, you can build the actual duct routing by assembling components from FHinfinity's built-in library, ducts, elbows, transitions, and more, ensuring the model matches your physical layout. To apply realistic fan pressure to the heater, you can also input the fan characteristic curve on the fan page, then set the operating RPM. This allows the solver to account for actual fan performance under varying system conditions. After running the model, the duct element report provides detailed results for each duct component, including velocity, pressure drop, velocity head, and other key hydraulic parameters. Additionally, FD fan datasheet in API 560 format is automatically generated. A similar workflow applies to induced draft fan configuration. On the stack layout page, if you've defined the type of flue system as duct end stack, you can assemble the induced draft zone ducting using components from the library and place the ID fan directly within that duct path. If your heater includes an air preheater, you can position it in either the forced draft or induced draft zone duct, or both. Initial APH parameters, such as type, burner inlet temperature, and leakage factors, are entered on the dedicated air preheater page. After running the model, FHinfinity generates not only the ID fan datasheet, but also a comprehensive APH datasheet. This report includes thermal performance data and other critical calculations like acid dew point temperature and minimum metal temperature, both evaluated based on the acidic components in the flue gas, helping you assess corrosion risk and ensure long-term equipment reliability. This integrated approach ensures that every major component of your heater system, from burners and ducts to fans and heat recovery units, is modeled with consistent engineering precision.